Yeah, so hi everyone. First of all, I want to thank the organizers to give me this opportunity to present my work. And I do apologize for not being able to attend the talks before mine, since my local time now is like 5:20 a.m. But I'm happy to share our work on all-electron Gaussian-based GW methods for periodic systems today. And this work is done together with Professor Gardner Chen at Caltech. Okay. I'm sure that speakers before me have already given great introductions to the GW method, but I just want to give you some background to set up the context for this talk. One of the most probably fundamental experimental techniques to characterize solid-state materials is photoemission spectroscopy, where in photoemission and inverse photoemission spectroscopy, by removing and adding electrons to the material sample, one can determine or measure the energy levels of valence band and conduction band of a given material, so that we could understand the band structure of a given solid, which is probably one of the most important electronic property of a material. And it's also critical for us to understand exotic quantum phenomena in correlated solids. For example, phase diagrams in the famous cuprate superconductors. And in theory, there is this one physical quantity that corresponds exactly to these experimental processes, which is a one-particle Green's function, written in the frequency domain. One-particle Green's function describes the probability of removing or adding electrons to your material sample. And by computing the Green's function for the material, one could get direct access to the spectral function, or more specifically, density of states. And the GW method is probably the most efficient many-body theory for simulating weakly correlated material spectrum. And to understand the GW theory, it's helpful to look at this diagram known as Hadding's equation, which describes an exact way to simulate a many-body system or a solid-state material. But we all know that in reality, it's not possible to really exactly solve any realistic material. Instead, numerical approximations always need to be used. GW is just one such approximation, where in this Hadding's equation now, this vertex correction is ignored, and only these four physical quantities are self-consistently updated. And more often, people are using its one-shot form, namely that the Green's function and screen Coulomb interactions are computed at the DFT level, and then to extract the self-energy from a one-shot calculation. Up to date, there are actually quite many GW computer codes for periodic systems that are completely or partly relied on plane waves. So here is just a very incomplete list of these GW codes. But here our purpose is to use instead Gaussian basis for periodic GW method. And the reason for that is the following. First of all, because Gaussian basis is local atomic-like orbital, it is very compact. Normally, one only needs maybe 20 to 40 functions per atom. And because of that, there's really no need for any virtual space truncation in periodic GW calculation. And because of that, this type of Gaussian basis is widely used for molecular systems, and particularly correlating methods such as MP2 or couple cluster theory. And the second reason is the local Gaussian basis gives a good support to all-electron electronic structure method, because it can, in principle, treats valence and core excitations on equal footing. And of course, it has its own disadvantages compared to plane waves. The biggest one is probably that it requires carefully generation of basis set and may be difficult to improve systematically. Before I talk about GW method implemented in Gaussian basis, I want to briefly talk about periodic electronic structure methods implemented using Gaussian basis in the PySCF quantum chemistry package, which is what we are using. So our basis is a translational symmetry adapted linear combinations of Gaussian orbitals. That means given any Gaussian orbital in real space, one could always apply some translational vector and then form a block wave, just like this plot. And such block wave is our computational basis for any methods in PySCF. And of course, for electronic structure methods, it's important that we could compute the underlying integrals for the computational basis, specifically electron repulsion integrals for correlating methods. And to efficiently compute that, we always use certain type of density fitting methods, specifically Gaussian density fitting, which means we never compute full center to electron integrals directly. Instead, we compute 3 center to electron and 2 center to electron integrals. And this type of schemes has enabled periodic DFT, Hartree-Fock, MP2, and CCSD calculations for solids with Brillouin zone sampling. And here I'm just giving you one example, which was published back in 2017, where the authors describes the possibility to use equation of motion coupled cluster theory to compute band structure for solids, for example, silicon crystal. And now back to the GW method. So the use of Gaussian basis set for implementing GW is not new, of course, because for molecular systems, it has already been implemented in quite a few computer packages. And here, our first step is to implement such methods for molecules in PySCF first. And we closely follow the implementations in FHI AIMS and also CP2K, where we adopt 2 so-called full frequency G0W0 schemes, namely analytic continuation AC or contour deformation CD. And after implementing these methods and benchmark against other packages, we go ahead to extend our method to the solid-state materials. And here, the benefit for using Gaussian basis is the consistency between molecular systems and solid-state systems. So we don't have to modify too much for the codes, that we could have the same schemes for solids. And the computational scaling of our method is the same as other conventional GW methods. And here I also want to mention 2 related works in this regime. The first one is a gamma-only Gaussian-based GW method in combination with pseudopotential implemented in CP2K. And the second one is a recent publication where the authors describes all-electron numerical atomic orbital based GW with K-point sampling implemented in FHI AIMS. Now, I want to show you some benchmark results for our methods. First of all, because we're using a Gaussian basis set, it's definitely important for us to look at the basis set convergence. And the special note here is that as far as I know, there is no really optimized Gaussian basis set for doing correlated calculations like GW in solids. So instead, we just choose Downing's CCPV-XZ basis developed for molecules, which is regarded as one of the gold standard basis sets for quantum chemistry. And first of all, in this figure, I'm showing you the GW at PVE band gap computed for silicon, diamond, and cubic zinc oxide. And here, by increasing the basis set size from so-called double zeta to triple zeta to quadruple zeta, we could see that for all these three materials, at least at the triple zeta level, we already get pretty good estimation of the GW band gap compared to the large quadruple zeta calculation. And that being said, it seems Gaussian-based GW band gaps converge quite quickly, even for the challenging case, zinc oxide. So specifically for zinc oxide, I think the audience probably have heard from the previous talk about it, where in this recent benchmark paper for plane wave GW methods, they also shown the need for thousands of plane waves to converge plane wave GW calculation for zinc oxide, where by using Gaussian basis set, it seems even at the quadruple zeta level, we only need about 159 basis functions per unit cell to have a fairly good estimation. Next, I want to show you the finite size convergence of our methods. First of all, in this plot, we just show the GW at PBE band gap without any finite size correction for silicon and boron nitride. And as you can see here, by increasing the K-mesh from 2 by 2 by 2 to 7 by 7 by 7, the difference in estimated GW band gap is huge. And even at 7 by 7 by 7, it's still quite far away from the extrapolated GW band gap, which is regarded the thermodynamic limit. And the reason for that is there is this leading source of finite size error in computing electron repulsion integrals, where there is really an integrable Coulomb divergence one needs to specially treat. And here, our strategy is to follow these two papers to apply certain finite size correction, also known as the hat and wings correction, where after applying this finite size correction to treat the Coulomb divergence, we find the band gap for both silicon and boron nitride are improved significantly at intermediate K-point region compared to the thermodynamic limit. And that being said, it seems we could get the TDL result for GW method by either using K-point extrapolation or Coulomb divergence correction. And after these benchmarks, now I want to show you a summary of the results for our GW band gaps of semiconductors and rail gas solids, where we're using a CCPV TZ basis. And as summary in this table or in this figure, you could see the agreement between GW and the experimental values is quite good, in line with the other plane wave implementations. And specifically, our GW at PVE result has only 5.2% mean absolute relative error compared to experiment for these set of materials. So in spirit of this workshop and this session, I think it's also interesting to sort of compare our methods with other GW implementations. And here I'm just showing some interesting analysis. One such a comparison is to compare against other local orbital-based GW implementations. For example, the recent numerical atomic orbital implementation in FHI Ames. And the other one is the LAPW plus high energy local orbitals based on FHI gap. The numbers here are just taken from these two papers. And here on the left side, we could see when comparing between Gaussian-based GW and NAO-based GW, we find, except for the zinc oxide case, it seems all the other materials, specifically semiconductors, have a band gap difference all within 0.2 eV. It's the same thing on the right figure, although on the right-hand side, the zinc oxide cases, the two methods have a much better agreement compared to the left one. And since the zinc oxide seems to be always a little bit controversial and important in the GW community, it's worthwhile to take a deeper look at this material. What we did is, first of all, to try to test our results using different Gaussian basis sets to make sure that our zinc oxide results are not affected significantly by the choice of different Gaussian bases. So here, in addition to CCPV-TZ basis, we also choose another Gaussian basis, namely DAF2-TZV-PP. And here, as you could see in this table, indeed, our method gives very consistent GW at PBE and GW at LDA band gaps between these two basis sets. And next, there's just one summary of comparison against other GW implementations. Specifically, in addition to these two implementations, I also include this plane wave-based benchmark very recently using these three packages. And it seems when comparing the zinc oxide band gap, our Gaussian-based GW method has the best agreement with this LAPW plus HLO method, where we find that our GW at LDA band gap seems to be around 0.2 EV larger than NAO-based and plane wave-based GW methods. And in addition to semiconductors, we also did a test on one metallic system, which is bulk copper. And here is just the band structure computed at the GW at PBE level using Gaussian-based GW method. And we could also do some comparison against other GW implementation. Here, we are comparing against the PAW-based GW implemented in VASP, and also compared against experimental values. And by computing these positions of different bands and also widths of D bands, we find at least our Gaussian-based methods perform very similarly compared to PAW methods. Even the mean absolute error seems to be slightly smaller, which indicates at least the Gaussian basis seems to be also reliable for doing metallic system GW calculations. Now I want to switch gear to take a few more minutes to talk about the core excitation binding energies for solids. So this is actually a quite natural target for our all-electron Gaussian-based GW method. because we could, in principle, treat both core and valence excitations on equal footing. And I also want to mention that there are already great explorations for using GW for computing core binding energies in molecules, specifically these two papers. And the authors have shown that at this partially self-consistent GW level, one could get quite accurate estimation of core binding energy in small and medium molecules. And here we are applying our periodic GW method to some semiconductors, where we are using two different DFT starting point, namely PBE and a hybrid PBE functional with 45% Hartree-Fock exchange. This number is actually taken from this JPC letter paper where I show you here. And the purpose here is just to try to mimic the EVGW0 result. And as you could see, by using our Gaussian-based GW method, we can see the GW method indeed improves significantly compared to their underlying DFT method, showing in this table. And particularly when we look at the use starting from the PBE 45, then the GW method only has around 0.6 EV mean absolute error compared to experimental values. And I think from this study, we think that although it seems to improve over DFT significantly, but it's also concerning because it has a very big dependence on the starting point. So self-consistency or partial self-consistency seems to be necessary for further improvement and more robust estimation for core binding energies. All right. Now, in the end, I want to slightly mention the use of our Gaussian-based GW method for other purposes. For example, in this recent paper published by Tim Berkelbach's group at Columbia and Flatiron Institute, the authors have used our GW code in the same setting, namely same Gaussian basis set and the periodic boundary conditions to compare against other quantum chemistry methods, MP2 and PEOM MP2 on a few semiconductors. This kind of framework enables us to understand better the performance of their newly developed PEOM MP2 method. And for our own purpose, we have used this Gaussian-based GW method in our recent ab initio quantum embedding framework, where we're trying to combine our GW method with dynamical mean field theory to describe the strongly correlated materials. And in conclusion, I have shown you a all-electron Gaussian-based periodic GW implementation in PySCF, which can, in principle, treat both valence and core excitations accurately. And a point that we felt quite necessary from this study is optimized Gaussian basis sets for doing periodic correlated calculations. And with that, I want to thank my postdoc advisor, Garnet Chen at Caltech, and also funding sources from US DOE and Simons Foundation, and also support from Caltech HPC. And thank you for your attention. I'm happy to take any questions.
Thank you very much for your presentation. So, any question from the audience? Yes.
Hello. Thank you very much for the nice presentation. I just would like to comment on the zinc oxide comparison you made.
Yes, please.
In your all-electron calculations, you completely neglect the relativistic effect. Whereas when we use pseudopotentials, implicitly, thanks to the pseudopotentials, we have some of the, let's say, the scalar relativistic effects that are included readily without even noticing it in the calculation, in the final results. So that may explain why you still have, let's say, 0.2 difference for zinc oxide compared to the other plane waves evaluations.
That's a very good point. Yes, indeed, we don't have any treatment of the relativistic effect. And yeah, in that sense, do you think there is like any way that we could try to estimate the quantity from using pseudopotential or from the relativistic effect?
In chemistry, you also have the ECP framework that are pseudopotentials, basically.
Yes.
And for zinc, I think you have some effective core potential that are published, and you may use this effective core potential to do pseudopotential calculations with Gaussians. And then I think this would be a more fair comparison with respect to what we do with plane waves.
Okay, that's a good suggestion. Yeah, I will definitely take into that. Yeah. Yeah, thank you.
Yeah, maybe if I may add one comment on that point as well. So if I'm not correct, I just checked, you're using contour deformation, right, for the GW and PySCF.
Yes.
In the comparison that that Fabien was talking about, this is all let's say plasma pole models still, right? So I think we no.
We
miss one?
first
Sorry.
Assessed everything with plasma pole model, and then some of the calculations, especially the one for zinc oxide. Right? In the end, it's a fully contour deformation as well. Is your code available in PySCF already, or?
Yes, our code is already available in PySCF. Yes.
Again, Fabien.
So sorry to insist. When you showed the integrable divergence in the exchange, you showed some results with no correction.
Yes.
So what do you call no correction? Do you just neglect the Q0 contribution?
Yes, correct. We just fully neglect the Q0 contribution, which is definitely not the optimal things to do. Yeah.
Yeah. Okay.
Yeah.
Thank you.